In this video, I'll be talking about the range and the null space. This is the first of two videos in which I'll be talking about the definition of these terms as well as providing some examples. First, let's talk about the range. Let f be a linear operator from the vector space x to the vector space y. So we have a space x, and f is going to eat elements of x and spit out elements of y. Technically, we call x the domain, and we call y the codomain. Now it's possible that f does not map onto all of y. F may only take elements of x and map them to a subset of y, and this we call the range of f. More formally, the range of f is equal to the set of all y in the vector space y such that there exists an x in the vector space x such that f of x is equal to y. Okay, so let's do an example. Let f be the mapping from R to R such that f of x is equal to 2x. You should be able to convince yourself that this is indeed a linear operator. So our domain here is the reals, and our codomain is also the reals. So the question is, what is the range of f? Well, by definition, it's the set of all y in R such that there exists an x in R such that f of x is equal to y. But this is just the set of all y in R that have an x in R such that 2 times x is equal to y. Or we can just say that this is the set of all y in R such that y is divisible by 2. But all real numbers are divisible by 2. So that means the range of f is R. Hence we see for this particular linear operator, the range is the entire codomain. Okay, now let's talk about the null space. Again, consider a linear operator f that maps elements of the vector space x to elements of the vector space y. So we have an x that looks like this, and f takes elements of x to the vector space y. Now, since y is a vector space, we know that it has a 0 element. The null space is focused on what elements of x map to this 0 element. So it is a subset of the domain. Formally, the null space of f is the set of all x in the vector space x such that f of x is equal to 0. Okay, let's go back to the example we had earlier, where f is a linear operator from R to R such that f of x is equal to 2x. Again, our domain is R, the codomain is R, and we're interested in the x that mapped to 0. So going back to the definition, the null space of f is equal to the set of all x in R such that f of x is equal to 0. But in this case, that's the set of all x in R such that 2x is equal to 0. But the only x such that 2x is equal to 0 is the 0 vector, so we're left with the trivial null space. So in this case, the null space of f is simply the set containing only the 0 vector. Now let's do an example looking at both the range and the null space. In this case, we'll take f to be a mapping from R2 to R. So now we're looking at the plane, and f is going to map to the real line. And f is going to be defined such that f of x is equal to the vector 1, 2 transpose x. So expanded, that's 1 times x1 plus 2 times x2. So the question is, what is the range of f, and what is the null space of f? Take a second to pause the video and think about it. So by definition, the range of f is going to be the set of all y in R such that there exists an x in R2 such that 1 times x1 plus 2 times x2 is equal to y. So if we let y be an arbitrary element of R, then we can notice that if we pick x to be equal to alpha 0, then f of x is simply going to be 1 times alpha plus 2 times 0, which is alpha. So we have found an x that maps to y for any real number. Therefore, the range of f is equal to all of R. Okay, so what about the null space? By definition, it's the set of all x in R2 such that 1 times x1 plus 2 times x2 is equal to 0. But this is just the set of all x in R2 such that x1 is equal to 2x2. This means that elements of our null space can take on several different forms. As long as x1 is equal to 2x2, we can choose any x2 we want and still be in the null space. This gives us a lot of freedom. So the null space of f is going to be alpha times the vector 2, 1, where alpha is any scalar we want. Here we have a non-trivial null space. In fact, this null space has infinitely many elements. So to recap for this example, remember that we found the range of f to be all of R1. And the null space of f is going to be any scalar multiple of the vector 2, 1. So it should look something like this. Notice that in this example, both the null space and the range of f contain the 0 vector. Take a moment to verify for yourself that both the null space and range are vector spaces, and in fact, that the null space and range of any linear operator is a vector space.